So welcome everyone. Today we are glad to have Zhiyi Huang as the speaker. Zhiyi is an associate professor of computer science at the University of Hong Kong. He did his PhD from University of Pennsylvania and then postdoc at Stanford University. And before that, he got a bachelor's degree from first Yao class under Andrew Yao in Tsinghua University in China. He has received multiple Best Paper awards, including Best Paper Award in Fox 2020, SPA 2015, and also awards like Early Career Award by RGC Hong Kong, Maurice and Dorothy Robinoff Dissertation Award, Simon's Graduate Fellowship in TCS, and so on. He has made seminal contribution in theoretical computer science. In online matching, for an example, in 2020 alone, he has published 4 or 5 StockFox breakthrough papers on matching. And this year again, there are multiple top tier papers on these topics. And one talk could barely cover them. So he has kindly agreed to give 2 talks. And today we'll have the first talk, and next week we'll have the second one. So again, we are extremely happy and excited for G's talk. G, all yours now.
Okay, thank you for the very generous introduction, and thank you for having me here. Okay, so this will be the first part of the 2 talks on some recent progress in online matching. And today's topic will be covering some general arrival models that is a generalization of what you may have known as the KBV, sort of the classical online matching model. So even though I choose the title to be sort of general arrival models, actually I have shamelessly choose to just focus on one model that I have been working on in the last few years. And only towards the end, I will give some pointers to other general arrival models for those of you who are interested. So let's see. Okay, so for this audience, I guess online matching or matching in general does not really need a motivation. Just think of the event that we all missed, traveling and going to conferences in person. So there will be some matching of passengers to flight seats and flights, and there will be matching of guests to hotel rooms. And when we search for trip information, you're all aware that there will be a matching between impressions and advertisers. So part of our search results are actually sponsored results. And when we get to our destination, when we need to call a ride from the airport to the hotel, then there will be a matching between riders and potentially taxis or self-employed drivers. So historically, online advertising has been the main driving force behind the literature of online matching for decades. So I'm going to use that as our running example for now. In this example, then we're going to have a bipartite graph. One side of the bipartite graph are advertisers. All of them are known to the system upfront. Now, on the other hand, we're going to have some impressions, which are basically searches by users. When each impression comes, the system can determine which advertisers are interested in the keywords. And we can potentially, for simplicity, show one ad to each impression. So let's say we just do it greedily and for a couple of rounds. And at some point, there might be an impression that comes, and the advertiser who is interested in this impression is already matched. Then at that point, we have no choice but to leave this impression or online vertex unmatched. And so on and so forth. So for simplicity, let's assume that we are only interested in the cardinality of the matching, which roughly speaking captures the scenario where all advertiser impression edges are worth the same. So in this case, the algorithm managed to get 3 edges. Now, of course, in hindsight, we can take the entire bipartite graph and run your favorite bipartite matching algorithm to find out that there's actually perfect matching in this graph. So the optimal benchmark will be 5 edges. And the ratio of the 2 is called the comparative ratio of the algorithm. But more precisely, we're going to do the worst case analysis. So the comparative ratio will be the ratio of the algorithm's matching size and the optimal matching size in the worst case graph and also the worst case arrival order. And this is the model introduced by Karp, Vazirani, and Vazirani more than 30 years ago. This is the online bipartite matching problem. And in the same paper, they pretty much solve this problem. They give a very elegant ranking algorithm. So what they do is that they're going to rank all the offline vertices randomly at the very beginning. And this is the same ranking that we're going to use throughout the whole process. And then whenever an online vertex comes, I just check which unmatched neighbor has the highest or smallest rank, then match to it. And just like before, if at some point, for example, the fourth online vertex on the right arrive, the only neighbor that it has is already matched. Even though there's an alternating path, we cannot regret it. So once a match happens, it's permanent. So we have no choice but to leave the fourth online vertex on the right unmatched. So what they show is that ranking achieve a 1-1/e comparative ratio, which is optimal. So here for a randomized algorithm, we're going to, when we compare the performance of the algorithm, of course, we're going to take the expected size of its matching and then compare it to the maximum matching in hindsight. Okay. And since KVV, there has been a huge literature on online bipartite matching, and many generalizations have been considered. And again, mostly because the motivation from online advertising. So for example, in online advertising, it is very natural to consider different advertisers paying differently. For example, an advertiser who is selling candy is likely going to pay less than, let's say, car dealers. So this would motivate the problem of offline vertex-weighted online matching, where each advertiser or each offline vertex has some weight. And instead of just maximizing the cardinality of the matching, now I want to maximize the sum of the weight of the matched offline vertices. And more generally, if the advertisers actually check the cookie information of different impressions, then even the same advertiser may want to pay differently for different impressions, depending on the level of match. And then this will motivate the even more general edge-weighted online bipartite matching problem. And also, there's a very famous work by Mehta, Saberi, Vazirani, also known as MSVV, who introduced the AdWords problem. So here, they basically capture the fact that each advertiser are willing to have their ad shown multiple times. It's just that they want to set a budget on how much they're going to pay, and then their actual payment will be a budget additive function, which means that it is going to be the either the sum of the values of all the edges matched to it, or its budget, whichever is smaller. So this is known the AdWords problem. For the last two problems, actually, we're going to cover them in a bit more detail in the second part of this talk next week. But the main message that I want you to take away from this slide is that all of these existing models assume that the graph is bipartite. So basically, there are two different kinds of objects, and one side of the bipartite graph is known offline. And this makes perfect sense in the case of online advertising, because we have advertisers and impressions, and advertisers register to the system upfront. So both assumptions make perfect sense. But I want you to convince you that if you move away from online advertising, then actually both assumptions could break. So for example, let's think about ride hailing, where we have an application that wants to match riders to drivers. Now, in this case, you can imagine that both the drivers and the riders basically show up in an online fashion. So both sides are online, even though the graph is still bipartite. And on the other hand, if we look at ride sharing, in which case we want to match different riders, and if two riders have similar pickup locations and similar destinations, then maybe they can share a ride, and we can serve them using the same driver. So here we are even simplifying the problem so that we are only considering the matching among riders, but not considering how to match them with drivers afterwards. So in this case, the graph is not even bipartite, because you can imagine that if A and B can be matched together and be served with the same taxi, and B and C can also be matched together with this and be served with the same taxi, then it is quite likely that A and C can also be matched together because, well, very likely they have similar pickup locations and destinations. So if you really want to introduce structural assumptions into the graph, then it is not bipartite, but more like sort of clique structure with few edges across different cliques. So in general, you can imagine this will be a matching problem over a general graph where the graph is not bipartite. So I think this kind of motivates or ask for a more general online matching model that can capture this kind of scenario, and hopefully it is a model that is interesting enough so that we can give some non-trivial algorithm for it. So for the remaining of today's talk, I would like to first introduce a model which we call fully online matching that will allow us to capture the two scenarios that KVV model fails to capture. And then there are two stages of research so far on this model. The first stage, we basically analyze the classical algorithm, like the ranking algorithm that I just described, and also another algorithm called water filling, and derive fairly tight analysis for those classical algorithms. And in the second stage, we go beyond the classical algorithms and show that actually for this more general problem, these classical algorithms are not the optimal one. So let's move on to the model. And by the way, please feel free to stop me and ask questions at any point if something is not clear.
So you'll continue to work with the adversarial arrival model, or like?
Yes, we are still considering the adversarial arrival model. So the graph will be arbitrary, and then also the arrival model, subject to some assumptions that I'm going to explain in just a second, is also adversarial.
Okay, so that element of KVV continues on.
Right. We're still doing worst case analysis, basically.
Okay.
Okay, so let me explain the model. So in the fully online matching model, unlike KVV, initially we know nothing about a graph. No vertices is known to the algorithm upfront. And then over time, there will be two different kinds of time steps. The first kind of time steps correspond to arrival of some vertex. So whenever a vertex V arrives, what the algorithm observes is the edges between V and all the previous vertices that have already arrived. And this is also the earliest time that we can match a vertex. So we're going to have a few vertex arrival, and at some point, we may also have the second kind of time step, which is the departure of some vertex V. And this is basically the last time that the vertex can be matched if it is not yet matched. So again, using the right sharing as our running example, then you can imagine the arrival and departure of a vertex basically set an active time window for each vertex. And when you call a ride, basically your request is active in the system for maybe 2-3 minutes. And then after that, it expires and you may need to resubmit your request. Okay, so and then before the departure of some vertex, in this case, it's the bottom left vertex that's departing, then this is the last moment that we can match it. So let's say we just match it greedily and so on and so forth. And then just like KVV, at the end, we just count the number of edges that we managed to match and compare that to the optimal matching in hindsight. And that would be our comparative ratio. There's just one assumption that I need to make about the instance. We're going to assume that the neighbors of some vertex V must arrive before V's departure. So in other words, there can be an edge between two vertices only if their active time window overlap. From a practical viewpoint, this would correspond to natural assumptions like we cannot match a rider in the morning to a rider in the evening, even when they have similar pickup location and destinations. And from a theoretical viewpoint, the algorithm by definition can never match such edges, so it wouldn't be fair to allow the optimal to have such edges. So this is the only assumption that we need to make when we say that the graph and the arrival model is arbitrary. Other than that, it's completely adversarial. Okay, so at the first glance, it's not even clear that fully online matching generalizes KBB because we introduced this new concept of departure of vertices, which is not there in KBB. But actually it does. So the KBB model is basically a special case where the graph is a bipartite graph and all the offline vertices essentially just arrive at the very beginning and they're super patient and only depart at the very end. And all the online vertices are basically the impatient vertices that arrive and then depart in the next step, so that you basically have to match them on their arrival. And that will capture the KBB online bipartite matching problem as a special case. So which also implies that this 1 minus 1 over E harness result from KBB also applies to fully online matching. Okay, so any question?
Just a quick
yes.
question.
Yes.
Right, so when a vertex arrives, its departure time is also known. It's not like a real time, as in your model, when V arrives, what's revealed to the online algorithm are its neighbors and its departure time. Or
so in our model, we do not assume that the departure is known, but we do assume that at the step when a vertex departs, we still can match the vertex at that very step. So yeah, so that's basically that's weaker than what you say.
Right, and it sort of makes sense to actually wait till the last minute for the.
Very good point. So due to our assumption that you can still match the vertex at the step that it departs, so it is without loss to consider lazy algorithms that only match vertices on their departures.
Okay, yep, thanks.
Okay, so so it generalizes KBB. So 1 minus 1 over E is still a upper bound, and a very simple observation is that greedy algorithm is 1/2 comparative, just like any other unweighted matching problems. So basically, the game is to really understand what is the best ratio between 1/2 and 1 minus 1 over E for this more general fully online matching problem. Okay, so this is what we know so far in one slide. So like I said, in the first stage of the research on fully online matching, we focus on the classical algorithm like ranking, which is a randomized integral matching algorithm. And there's also another classical algorithm called water filling, which is a deterministic fractional matching algorithm that allows you to match the same vertex fractionally to multiple neighbors as long as the total match amount sum up to most 1. Both algorithms are 1 minus 1 over E comparative in the KBB model, which is optimal. And the takeaway message for these classical algorithms is that they still work reasonably well. They beat the 0.5 trivial ratio achieved by a greedy algorithm. So for bipartite graph, we give a tight analysis for ranking and show that the comparator ratio is something called the omega constant, which is roughly 0.567. And for general graph, we also give analysis that it is better than 0.5, but this number likely is not optimal. So there's no point to really remember this number. For water filling, what we show is that for both bipartite graph and general graph, you can get 2 minus square root of 2, which is 0.585, and this is tight. So one thing that I want to point out is that in fully online matching, it seems that water filling is actually outperforming ranking, which is something that you don't see in the classical model. Just an interesting observation.
So one question.
Yes.
In the general graph, what is the lower bound? Is it 0.567? So 0.521 is the best algorithm. What is the best lower bound there?
That's what I'm going to cover right now. So we also show that actually not even general graph, just on bipartite graph, as long as you allow this fully online arrival model, then it is strictly harder than the KBB model in the sense that we show a hardness that is marginally smaller than 1 minus 1 over E. But I won't cover this hard instance because I don't think there's any insight to it. We just achieve it by trial and error and calculation. But it is strictly harder than KBV. That's the important thing. And again, the hardness actually applies to just even if you only restrict your attention to bipartite graph. Okay. And then sort of towards the end, I'll give a brief introduction of some algorithm that is beyond ranking and water filling. That again, the conceptual message is that they are strictly better than ranking and water filling. So somehow for fully online matching, these classical algorithms are no longer the optimal one, which is kind of surprising, at least to experts in online matching, because at least in all the generalization of KBV that I'm aware of, and for which we know the algorithm for, the optimal algorithms are always just variations of ranking and water filling with some modification. But for fully online matching, it seems that we actually need new ideas. And there's actually a very simple observation why we may need new ideas, but I'll cover that at the end. So again, the numbers are likely not tight, not optimal. The only thing important about them is that they are strictly better than the classical algorithms. Okay, so now, any question before I move on to the sort of the technical part of today's talk? Okay, in that case, I'll just move on. So for the technical part, I'm going to spend the main chunk of time to cover the analysis of ranking on general graph, because I think that's the part that really need at least one new idea that is likely useful also for other matching problems on a general graph. So that's something that I really want to cover. So let's recall what is the ranking algorithm. For the KBV model, what it does is that I'm going to draw a random permutation over all the offline vertices. And then whenever an online vertex arrives, I'm going to match to the first unmatched neighbor according to that permutation. So that's the ranking algorithm. Okay, now there's no such thing as offline vertices. All the vertices are arriving online, and all of them can be matched as if they are chosen by some other online vertex. So to generalize this, the natural generalization is to draw a random permutation over all vertices. And then, like as remarked before, it is without loss to consider lazy algorithm. So I'm going to wait until the departure of some vertex. And then I'm going to try, if that vertex is not yet matched, I'm going to try to match it to the first unmatched neighbor according to the random permutation that I choose at the beginning. So that would be the ranking algorithm for fully online matching. So I think in case some of you are wondering, it seems that ranking algorithm is not even well defined because all the vertices are online. How can we draw a random permutation over them right at the very beginning? I don't know what vertices are there. So it really boils down to a simple trick that is actually known even in the classical model. So instead of drawing a random permutation, it is equivalent to draw a random number between 0 and 1 uniformly at random on the arrival of each vertex v. And then that would be the rank. And then essentially I'm sorting all the vertices in ascending order of this fractional rank y. And that is equivalent to drawing a random permutation over all the vertices. So in this example, I have a bunch of vertices that arrive. And then for each one of them, I'm going to draw a random rank as given inside the vertex. And then when the bottom left vertex needs to depart, I'm going to look at its 3 unmatched neighbors, and the top right one, has the smallest rank. So I'm going to match it to that one. So that would be the ranking algorithm. Just to remark why smallest rank has the highest priority, because in the past when I gave related talks, sometimes people ask about this. I think the reason is that we want to interpret the fractional rank, roughly speaking, as the integral rank divided by the number of vertices. So when we talk about integral rank, rank 1 is the highest priority. So that's why we let the smallest rank have the higher priority. But of course, you can do the mapping and do it the other way around. Okay, so now we have the algorithm. How do we analyze it? We're going to follow the gain sharing plan, also known as the randomized prime module framework by Devanu, Jane, and Kleinberg. So whenever a match happens, let's say some edge UV is matched, and this is matched because of U's departure. Because remember, we only match vertices as sum of the vertex departure. And then in this case, we consider U active, as in it's actively check all its unmatched neighbors and select one of them. And V is the passive vertex. So intuitively, active vertex is similar to the role of online vertex in the KBV model, and passive vertices are similar to the offline vertices in the KBV model. The main difference here is that the same vertex could be active for some edge and passive for some other edge, whereas in KBV, each vertex has a fixed role across all the edges. And then I'm going to have some non-decreasing gain sharing function G, which will be optimized in the analysis. And then when this match happens, V, which is the passive vertex, is going to determine how much it keeps by its rank YV. So G of YV is what V keeps. And the remaining 1 minus G of YV is what goes to U. So in total, 1 unit of gain will goes to the 2 endpoint of the edge. Now you can see that because G is non-decreasing, so by matching to the vertex that has the smallest rank, U maximizes its own gain. So we can also interpret ranking as just each vertex setting a random reserve price for itself, and whenever a vertex needs to depart, it just picks the neighbor that has the lowest reserve price so that it maximizes its own gain. And then now the plan for the gain sharing or randomized prime module analysis is really to establish the following inequality. It says that for every edge UV and the comparative ratio gamma that we try to show, we want to prove that the expected gain of the 2 vertices, U and V, sum to at least gamma. Now, why is this sufficient? Well, since every time an algorithm gets an edge, I simply split the 1 unit of gain between the 2 endpoints. Counting the total size of the matching by the algorithm is the same as counting the total gain across all the vertices. Now, instead of counting the gain on a vertex by vertex manner, I can instead go over all the edges in the optimal matching, and for each edge, I count the total gain accumulated by its 2 endpoints. Now, since this is a matching, I count each vertex at most once, and I may potentially drop some vertices if some vertices are unmatched. And then the inequality that we plan to show will ensure that each of this term is at least gamma in the summation. So this is at least gamma times the size of the optimal matching, and that will establish the gamma comparative ratio that we want. So, so the whole game is to design this gain function appropriately and also find a way to bound the gain that we give to the vertices so that I can establish this inequality. Now, to bound this, the whole process is very complicated because we have a random rank for each vertex. To make things tractable, actually, we're going to even fix the ranks of all the vertices other than U and V arbitrarily and show that over the randomness of U and V's ranks alone, this inequality still holds. So that will allow us to reduce the dimension of randomness down to 2 to make things a little more tractable. So for those of you who are familiar with KBV, this is actually basically identical to the KBV model. And I'm going to remark when we actually depart from the standard analysis. Okay, so some important concepts also translated from the KBV analysis. So first of all, monotonicity. There are 2 bullet points. The first bullet point basically says that if V is active or unmatched, so once again, V is active, meaning that it didn't get picked until its deadline, and then at its deadline, it actively chooses an unmatched neighbor to match to. And if in case it waits to the deadline, but all the neighbors are already matched, then it is unmatched. So both of these states essentially indicates that the rank of V is large enough that it's so unpopular that no one picks it before its deadline. Then it says that if V is currently not so popular, then further increasing YV, or in other words, making it even less popular, will not change the matching at all, because V is going to still stay as active or unmatched, and everything that happens does not depend on the actual value of YV. And on the flip side, if the current rank of YV is small enough, or in other words, V is sufficiently popular that it's passive or being paid by some other vertex before its deadline, then further decreasing YV will make it even more popular, and therefore it will remain passive and remains paid by some other vertex before its deadline. So this simple property motivates the concept of marginal rank. So because of the monotonicity, you can imagine that there's some cutoff threshold theta such that when V's rank is above theta, meaning that it's not as popular, then V is either active or unmatched. And when V's rank is smaller than theta, meaning that V is sufficiently popular, then it is going to be passive. The point here is that these states will not change back and forth. It's only one transition point theta that we need to worry about. And to visualize this, basically, if I only look at try to capture these matching state as how its rank changes, then this is what it looks like. Now you can imagine that the typical worst case.
You've also,
yes, please.
You've also fixed so Y values, or the rank Y values of all other vertices except V are fixed here.
Okay,
including
good point.
U.
Yes, let me explain this. So in the actual analysis, we need to consider the randomness of the rank of U as well, basically the other vertex that we are worrying about. But since today I'm not covering the whole analysis, for the intuition that I want to give, I'm actually even fixing the rank of U as well.
Okay.
But in the actual analysis, we need to consider that.
Thanks. Yep.
Okay. Okay, so again, when the rank is smaller than theta, V is passive, in which case we know exactly how much V gets, right? Because it's just G of its rank. And when V's rank is too large, it's active or unmatched. And you can imagine that in the typical worst case analysis, the worst case that we need to worry about is really V is unmatched when it's not so popular. Because when it's active, it gets some gain. But when it's unmatched, it gets zero gain. So the typical worst case scenario is really that below this threshold, or like greater than this threshold, V is unmatched and gets zero. So what you can see here is that V's matching state and also how much gain that it actually gets is completely characterized by the concept of this theta. It's just the integration from 0 to theta, G of Y. That's it. The more challenging task is to come up with a handle to bound how much U gets. And by the way, U, again, it's the vertex on the edge that we are trying to analyze that departs earlier, because U is the active one with respect to this edge. Okay, so now let's try to characterize U's matching state depending on V's rank. Let's start with the easier part, when V is not so popular and basically stays unmatched. Now, in that case, either U is passive, meaning that it didn't get to wait to its deadline, it is already picked by some other vertex, which is a good thing, which is the left-hand side case. Or if U managed to stay unmatched until its deadline, then we know for sure that V is available. And moreover, we know that U did not pick V, which means that it has a better option. And that option is better than V all the way until V's rank reaches theta. So it means that the better option Z must have a rank that is less than or equal to theta. So in sum, when V is not so popular, we can claim that U is either passive or is at least as good as being sort of actively matching to V. So that's the gain that we give U in this regime. The task is more challenging when we consider the case when V itself is sufficiently popular. Can I go forward? Okay. Yes, so V use match when V is sufficiently popular. So by definition, V is going to pick by some vertex, let's say the top right vertex. And then meaning that this green vertex originally matched along the dashed edge to the first red vertex on the left, now matches to V. Now the availability of this first red vertex on the left may further triggers another green vertex to match this red vertex, and in total, I have an alternating path. Now the main point in the KVV analysis is that, well, this whole alternating path is from the every green vertex point of view, the alternating path happens because there's a newly available neighbor, and I opt to choose the new neighbor. So for some appropriate notion of better and worse, you can argue that on this alternating path, all the green vertices on the right actually gets better. Now, if the graph is bipartite, then I know that either U is not on this alternating path at all, which means that U, of course, is just like the old matching, or if U is on the alternating path, it has to be on the right-hand side, and therefore U only gets better. So in sum, when I can still use the bound that we get when V is not so popular, when YV is greater than theta, and use the same bound for the other region when YV is more than theta, because if anything happens to U compared to the other case, well, it's getting better. And indeed, for bipartite graph, even in the fully online matching model, we just follow this very standard analysis. Even though we get different numbers at the end, the whole thing is very standard, at least to experts. The real challenge comes when we try to analyze general graph. Now the problem here is that U need not be on the right-hand side. U could be one of the red vertices on the left, and in fact, you can actually argue that all the red vertices on the left are getting worse. Again, for the same appropriate notion of better and worse. And in the worst case scenario, U could be the last vertex in the alternating path and changes from being matched to unmatched. And that's indeed the most challenging case that we need to worry about. And in fact, if we just follow the O analysis using the gain sharing function G, and we can show that it doesn't matter how you choose the G function to be, you don't get a analysis that give anything better than 0.5. So what that says is that we need some new charging or gain sharing mechanism that will allow us to fix this problem. So in the next 5 minutes, I want you to consider the following typical hard instance and then explain the main idea of the main gain sharing mechanism that allow us to get the better than 0.5 analysis. So the typical hard case is that, first of all, V is unmatched whenever it's not so popular, when its rank is greater than the threshold theta, like I said, and V is passively matched by some vertex W whenever it's popular enough. And then moreover, when V is popular enough, the alternating path that it triggers has U as the last vertex on the left, and therefore U changes from being matched to unmatched when V is sufficiently popular. And that's a typical hard case that we need to understand. Now, by staring at this typical hard case for a really long time, we realize that there's something about this vertex W, the first vertex on the right on this alternating path. So first of all, W is really the reason for V's mystery when it's not so popular. Our claim here is that even when V is not so popular, let's say its rank is above theta, if W is removed from the graph, then V would still get matched. Now here's the reason. Assume for contrary that V stays unmatched. And we know that W is also not in the graph. It has been removed. So from the other vertices point of view, the whole matching process is the same as when V and W get matched to each other, because they just don't get into the matching of the other vertices. So what's happening when V is not so popular and W removed, then we're going to have this solid matching. It only departs from this solid matching when we reach its U's deadline. So in the solid matching in the original graph, U has no other available unmatched neighbor and therefore becomes unmatched. But now in the imaginary scenario, when W is removed, V is actually still there. So at that point, when we get to U's deadline, U would have choose V. Okay, so the point here is that if W is removed, then V is actually in good shape. It says that it doesn't matter how unpopular it is, it always gets matched. It always has U as the last resort who would pick V on its deadline. And furthermore, as I'll explain in the next slide, W itself is actually in great shape. It not only satisfies the inequality that we want for every edges adjacent to it, it actually satisfies them with some slack. So we can afford to let W send some compensation to V to help out. So that's the main mechanism. So more formally, let me define this concept of victim and compensation. So we say that V is a victim of some other vertex W if the following condition is satisfied. V is an unmatched neighbor of W, and V would have gotten matched if W is removed. And if this is the case, then our new charging channel will let W send some compensation based on its own quality of match. So if W matched to some vertex X, then depending on the rank of that vertex, I'm going to send H of YX to its victim. And W only get to keep the original amount of gain minus the compensation that we just defined. Now, instead of going through the calculation, which is not so insightful, let me try to explain a few high-level points. First of all, why isn't W itself in trouble? Why it has the room to send some compensation and still not run into trouble? Now, let's recall why U and V run into trouble, or what's the typical hard instance that we're considering. So first of all, U and V have no unmatched neighbors other than each other in the analysis. Otherwise, we wouldn't have this this scenario when, so for example, if V itself has an unmatched neighbor, then when its rank is above its threshold, then it wouldn't be unmatched. It can at least actively match to that unmatched neighbor. Now, on the other hand, if U has another unmatched neighbor, then U wouldn't be the last vertex on the alternating path. Okay, so for them to be in really deep trouble, they have no other unmatched neighbors. And second of all, in the analysis, we assume that U and V never matches each other. So these are at least some necessary conditions for us to run into trouble. And I want to claim that W is actually not satisfying these two conditions, at least not always. So consider any edge W and X. If X is V, the special neighbor that we're considering, then by definition, W sometimes matches V, because that's how it triggers the alternating path in the first place. Now, on the other hand, if this edge is not from W to V, but to some other vertex X, then we know that at least sometimes V can serve as a unmatched neighbors other than X. So in either case, we break one of these two conditions that actually make the analysis hard. So W is never in deep trouble, and that's why we can afford to send some compensation elsewhere. Now, some other concerns that you may have, for example, how many victims could an active vertex be? So even if W has some room to send out compensation, if I need to send it out to 1 million different victims, then probably it's not going to be very helpful. But a very simple observation is that there could be at most one victim for each vertex, because well, the removal of W triggers an alternating path, and at most one vertex can change from unmatched to match on the alternating path. So this can be at most one victim. And the second concern that you may have is that even though maybe U and V are receiving some compensation, but what if they also need to send some compensation elsewhere? Then the whole analysis becomes very subtle. But we can observe that if U and V are in trouble, then they never need to send out compensation because, again, they're in trouble because they don't have any other unmatched neighbor. And for it to have a victim, it has to have some unmatched neighbor. So the two conditions that in the definition of victims actually rule out these two concerns. And finally, my co-authors, Zhiyi Huang, Xiaowei Wu, and Yuhao Zhang actually managed to use a very similar victim compensation argument for another randomized greedy matching problem that also considered general graph. So I think this kind of analysis framework could be useful when you try to analyze algorithms on general graph. So in case you run into similar issues where the monotonicity property fails on general graph, then maybe you should consider this mechanism and try to use it on your own problem. Okay, I think I'm sort of running a little slower than I expected, but in any case, is there any question about this part? I think this is the main technical part I want to cover.
So you still have this this similar guarantee that the expected value of the these alpha u plus alpha v is at least this gamma. So it's not like another way of
We're still showing the same inequality. It's just that now the gain sharing is not just between the two endpoints. Sometimes the gain actually, a small portion of the gain also go to another vertex that is the victim of one of the two endpoints.
Correct. And so in a sense, it's sort of a relaxation that, I mean, the proof that you had needed only this alpha v's to sum up to a large quantity on average. And now, so in a sense, you're saying that even if alpha u plus alpha v is small, there'd be a w that will be able to compensate. Of course, this is the better
of course,
accounting.
W itself is getting less, so we need to make sure that the edges adjacent to W, they are not in trouble.
And the fact that like alpha u plus alpha v was 1, it's not a concern because it'll go up. Like, I guess, so if you go back to the slide where you had this.
Well, they sum up to 1 if that's the edge that gets matched, right? But it's not true that they always sum to 1. But the typical hard case, basically U and V almost never match to each other.
Okay.
So that's the typical hard case that we need to worry about. Yeah, if they match to each other, we're happy because we get 1 in this inequality. Yeah.
Okay, makes sense. Yep.
Okay, so yeah, so for the remaining part, I'm going to only cover very high level message. So for water filling, let me at least explain the algorithm. So now we are in the world of fractional matching. So for in the KBB world, then for every online vertex, I'm going to try to match this vertex essentially epsilon by epsilon bit, or like continuously match this vertex to whichever neighbor that is the least match, or the current match level is the lowest. And the technical term that they use is the water level of that neighbor. So it comes from the analog that each vertex holds a bucket that can keep 1 unit of water, and each online vertex comes with 1 unit of water, and the water just flows to its offline neighbors, whichever has the lowest water level. That's the analog that they're using. And then you can run the same algorithm for fully online matching. So again, whenever a vertex reaches the deadline, well, part of it may already be matched passively. But then if there is any unmatched portion of the vertex, then I'm going to match them continuously to the least matched neighbor. That would be the most natural generalization of order filling. So for example, the first vertex count, then it matched the 3 neighbors all up to 1/3. And then when this vertex reached the deadline, 2/3 of the unmatched portion go to its unmatched neighbor. So basically, the bottom right 2 vertices also get matched up to 1/3. And the whole analysis of water filling can also be done under the skin sharing framework. So essentially, now the price that each vertex set no longer depends on this random rank, but it depends on its current match level. And the intuition is that initially, when I'm not matched at all, I'm going to set a very low reserve price for myself so that I'm popular and want to get matched more. And if I'm already close to fully matched, then I'm going to set a very high reserve price. And I don't really care whether I get even more matching unless you're willing to pay me that amount. And then again, we want to show that, well, actually, in this case, there's no expectation because the whole process is deterministic. So I want to show that the gain of U and V sum to at least gamma for any edge in the graph UV. The analysis for water filling is standard, just like in KVV model, which why I'm skipping. I want to jump to the algorithm beyond the classical ones. And that's where some interesting ideas that I want to cover. So as I said, like ranking can also interpret as just setting prices according to this random rank, and each vertex picks the neighbor that has the lowest reserve price and then match to it, right? And then water filling is also setting a price according to its current match level. Or if you will, you can set a price according to the probability that I'm already matched. And then I just pick the vertex that has the lowest price so that I get maximize my own utility. And according to our analysis, water filling seems to be doing better than ranking, right? So we just try the most natural idea. We want to set 2 prices, one according to a random rank, and the other according to the water level, in which case is the probability that the vertex is already matched, and take the hybrid price. But the interesting thing here is that when we say we try to set the water level price according to the probability that V is already matched, this probability is changing over time, right? Initially, the probability is 0, and towards the end, the probability is maybe closer to 1. So which of this probability are we using when we try to set this hybrid price? Well, the first thing that you would try, which is more natural, is the beforehand water level. So basically, at use deadline, I look at what's the probability that V is matched before use deadline, right before use deadline, and that would be my water level. But our analysis shows that actually this is the wrong choice. You want to sort of look ahead. You want to set this water level to be the probability that V is matched after use deadline. Now, some of you may say, okay, you're cheating, right? I mean, you're using a circular definition. Well, how you set the water level here changes how likely V is going to be matched in this round, which will affect this probability that is matched after the deadline. So why is the algorithm well-defined in the first place? Now, the idea here is that actually this algorithm is not only well-defined, and you can approximately implement it, apply high accuracy in polynomial time. And we do this by running a deferred acceptance-like algorithm. We first overguess the look-ahead water level to be 1 for all vertices, and just simulate the algorithm and see what's the exact match probability for each vertex with this overestimation, and then find the vertex that has the largest gap and try to decrease its guess by some absolute amount, some appropriate absolute amount. And we show that this process terminates within finite time, such that the guess and the actual match probability are very close to each other. So I think that's the main idea that's needed. Other than that, it's just labor work to make everything work. The reason why look ahead water level is useful is that, let's say, if we try to analyze how much gain that you get by passively being matched from starting from 0 and after n rounds up to xv of n, right? So the amount of match happens in round I, or I plus 1 rather, is the difference between xv I plus 1 and xv I. And the price that you set is f of XVI, which is the lower end of the water level if we use beforehand water level. But with look ahead water level, what we get is the f of x of v I plus 1, the larger, like larger reserve price on the endpoint. And the point here is that if with look ahead water level, I can down this gain using the integration from x 0 to the final water level, the reserve price that you set along the way, which is the invariant that you actually want. Whereas in the beforehand water level, all you can, the worst case scenario is that you actually get matched all the way up to the final water level, or setting the price f of 0, which is very low, and that's too small for the analysis to go through. Okay, so let me just, for the last one, I'll just explain the algorithm. So for the fractional matching, instead of running water filling, the improvement comes from the observation that if the two endpoints of a vertex, the two endpoints of an edge sets some reserve price that is less than 1, meaning that they each want something that's sum to less than what the edge can offer, then there's actually no reason to wait until the deadline of either vertex. You can directly match them together, even when the edge first comes. So the eager water filling is going to match vertices both on their arrival and at the departure. On the arrival, I'm going to continuously match to neighbors with lowest water level, as long as the reserve price sum to at most 1. And then only after that, I'm going to run the usual water filling algorithm. And if I actually reach the departure of some vertex and there's still some unmatched portion, then I'm going to match to the neighbor with the lowest water level. And the intuition why this is helpful is that water filling actually ignores a very important piece of information, which are the edges among vertices that have arrived but not yet departed. So you can imagine a harder model where an edge becomes visible to the algorithm only when at least one of the endpoint departs. And water filling is actually well defined even in that harder model. But intuitively, these pending edges should be important too, right? Because when I'm trying to choose several unmatched neighbor, and one of them has already a zillion other neighbors that have arrived and not yet departed, and another one has no other unmatched neighbor, then that should tell me something about like which one to choose, right? But water filling completely ignores that information and simply look at how much they have already been matched, but in some sense ignore the future match potential that is indicated by this unmatched, these pending edges. And eager water filling sort of implicitly utilize this information, because if you have a zillion neighbors who have arrived, then quite possible some eager matching has happened, and therefore this vertex would have a higher water level to begin with. Okay, so just to sum up, today we talk about this fully online matching model where the graph is completely unknown at the beginning, and we have the arrival of a vertex, at which point we see the edges incident to the existing vertices, and also the departure of vertex, which is the latest time that we can match a vertex. And beyond this model, there are also some other models with general arrival. For example, the general vertex arrival model, which is similar to fully online matching, except that we can only match a vertex on its arrival. Sorry, we can only match an edge when one of its endpoint arrives. So there's no departure of vertices. And you can see the references here, and there's the even harder edge arrival model, where the graph just reveals to you edge by edge, and when an edge arrives, you need to immediately decide whether to choose it into your matching. And that's the online window matching problem, which is again very similar to fully online matching, but they make two different assumptions. First of all, they assume that the vertices are follow first in, first out, which makes a lot of sense in the ride-sharing model, because each request essentially stays in the system for roughly a fixed period of time. So they thus satisfy first in, first out, at least approximately. And they, because of this additional assumption, they're able to handle the edge-weighted case, which also makes a lot of sense in ride-sharing, because different rides are worth different amount of money. And this is the table. And let me just save some time in case some of you still want to ask questions, since I'm already overrunning. And let me stop here. Thank you for your time.
Thanks, Zhiyi. So can you go to the balance ranking algorithm once more?
Okay, sure. The balance ranking algorithm. Sorry. Yes. Should I go to, yeah, maybe this side? Or do you want to go to the slide before that?
The integral, like finally we are giving an integral matching.
Right. At the end, I'm giving an integral matching. So xv of xv is actually the probability that v is matched, not whether it's matched or the sort of fractional match level.
It's a randomized algorithm, and that is the probability.
Yes. So we're taking the ranking component as sort of a way to introduce randomness into the algorithm, and then we're trying to use the water filling price as a way to calibrate the ranking decisions.
Yeah. So my confusion was water filling is more like a fractional variant. So that's what I was confused. Is it a fractional?
Yes. Water filling on its own will be a fractional variant. So for example, if you run this algorithm without the ranking component, then all the water level will be binary, and it's not really giving you any information at all. So somehow, even though we know that water filling is doing better for fractional algorithm, I cannot really set the G component to be 0. I need some way to introduce randomness into the picture.
A couple of more questions. So what about special models like with recourse or random order arrival? Any of these techniques do you think will be helpful there, or what are the bottlenecks that you face?
I still haven't found a way to really introduce random arrival into fully online matching in a reasonable way, because of this assumption that the edge can only exist between two vertices with overlapping time window. So if you fix the graph, right, then you cannot truly make the arrival and departure random.
Right.
So that's something that if there's some reasonable way to define a random arrival model, that would be very interesting. And I believe we can get much better ratio.
And for the edge arrival, what is it, based on 2 minus epsilon or something, or like recently there was some.
Actually, so yeah, let me mention that. Sorry, for edge arrival, actually, there's the latest progress is the harness result. Unfortunately, they show that 1/2 is essentially what you can get. You cannot do anything better than that. They're only on special graph. There are some studies on special graphs where you can get some ratio better than 0.5. But for general graph, you cannot do anything better than 0.5. But for general vertex arrival, then this Wang and Wong gave a fractional matching algorithm that is essentially 0.52 competitive. And this paper in 2019 gives a 0.5 plus epsilon competitive ratio for some very small constant epsilon.
Right.
Yes.
Any other question?
So just like a slightly maybe a slight digression, but so this the very naive sort of greedy algorithm is a point, like is a absolute guarantee, as in it's 0.5.
Right, 0.5. Yes.
Yeah. So in these like in these randomized algorithms, let's say the ranking
Right.
one. So are there like high probability bounds interesting? So beyond, of course, like the 0.5
Right.
thing.
I'm not aware of high probability bounds, but on the other hand, in simulation, they seem to concentrate.
Okay.
That like they're like not too far from one minus one over e most of the time. But I don't have a sort of a theoretical analysis for that.
Right, and even like yeah, so because the margins are like not.
Yeah. So you're right. The margin is not like huge, so it would be nice to have hyperbolic bound, but I'm not aware of any of that. And at least the analysis framework fundamentally sort of only consider expectation. So
Right.
it's unclear how to approach that in the first place.
Yeah, but for the applications, I guess this is good enough. Like if you're for like a company like running this.
Yeah.
This is on average is good enough. Yeah.
Right. And actually, like if you're really running it on real graphs, and typically it's much better than 1 minus 1 over e. Anyway, I remember reading a paper who basically evaluates a lot of different online matching algorithms, and I think it's more like 0.8 something compared to on real instances.
Yeah, this is big, like a lot of dollars. So these.
Yeah.
Yeah.
Yeah, and I imagine that on like for online advertising, there will be a lot of stochastic informations or predictions that you can use. It's like worst case analysis only give you so much, but
right.
It's important to use those information.
And is there like the fractional results? Like so, I guess in the offline case, the fractional optimal and the integral optimal collide, but in the online, like they are distinct. Like the gaps kind of highlight that.
Right. So I think so. First of all, for online bipartite matching, we know that there's no gap. Both version gives 1 minus 1 over e, unless it insists on using deterministic algorithm. Then of course there will be a gap. But for fully online matching, the evidence that we have collected so far seems to suggest that there might be a gap, but we don't have a proof.
And so, is there some results of the form that, like, if it's a large enough gap? Again, I'm wondering if the fractional can be interpreted as a probabilistic assignment or.
Yeah, it's kind of also related to what I'm covering next week. So I think like so back in the days when Devanu, Jane, and Kleinberg introduced this randomized prime module analysis, I think that the motivation is trying to really understand ranking as a rounded algorithm of water feeling, but they ended up getting something else. So I think now, at least in my opinion, ranking is not a rounded solution of water feeling, but it might still be possible to come up with some online rounding method that can round fractional algorithms to get integral algorithm, which is related to what I'm going to cover next week.
Okay. So I'll wait for that. Okay, thanks.
So another question I have is regarding this algorithm of balance ranking and eager water filling. So do you think this analysis is tight, or like what is known about the hardness of this?
I don't think they're tight. I think like they are interesting only because of this conceptual point that classical algorithms are actually not optimal. And yeah, so my conjecture is that you can actually improve a lot on top of this, but like technically it's very difficult. Like I don't even want to suggest that these are the right algorithms to begin with. Like you can see balance ranking is kind of ad hoc. We just say that, okay, water feeling is better than ranking. Let's try to use that information to calibrate it and improve it by some absolute amount, right? Really like only improve by 0.002. So that cannot be tight.
But I mean, at least the analysis, do you think it's tight or?
No. Even for the algorithm, I don't think it's tight. Like we try to fully optimize the function, the price function G and F under the analysis framework that we're using, we essentially just optimize it numerically up to high accuracy. But then, like, that only says so much about the framework that we use. I don't think it's tight.
Thanks. Any other questions? Yeah, otherwise, let's thank the speaker. It was a great talk. And yeah, next week again, we are looking forward to your talk again.
Yeah, thanks.
Thank you all for coming, and talk to you next week.
See you. Bye.
Bye-bye.